Is the screen visible?
Yes, sir.
Yes.
Okay. Okay, let's begin. A central question for any machine learning researcher is to test if the hypothesis formed is good. Will it stand the test of future unseen data? This is a primary question in the mind of any machine learning person who uses data and forms hypothesis about the data. So we had done hypothesis testing before. Now, since there are many new students in the group, I thought it will be helpful to revise whatever has been done before. And even for those who have heard these lectures on hypothesis testing, it doesn't harm to go back to those concepts because they are so foundational. Now, let me go ahead and start the discussion with an NLP problem, and two more problems will be taken. They were also discussed before, and the group has seen those problems. Just as a reminder, these lectures are not like class lectures. There is no quiz, no exam, no assignment based on this. These are for academic enjoyment, and our goal is to build a solid understanding about the concepts and apply them in our research. So the NLP problem, many of you will be familiar with this statement of the problem. In fact, an assignment is being done in the class now on named entity identification. So here is the situation. 50 words have been given to the named entity identifier. Okay, Swarup says, is streaming working? Are you able to see? Yeah, okay, Tejpal says yes. Yeah, see and hear me. Maybe Swarup, you should rejoin. Join and rejoin. Disconnect and reconnect. Okay, so this is this assignment is something the CS626 class is working on now, and we have created a name entity identifier. It has been given 50 words, and 32 words out of those 50 have been tagged correctly. Now, based on this, we claim that the accuracy of the system is 64%. What it means is that in future also, this accuracy will be maintained. That means if I give a 1,000-word test corpus, then at least 640 of those words will be given correct named entity identification tag. That tag is binary 0 or 1. Is the token a name or not? Okay, this is the binary decision. So we have got this observation, 32 words out of 50 have been tagged correctly. And we are jumping to a conclusion, okay, that the tagger has 64% accuracy. You can immediately spot the fragility of the situation. Only one sample has been taken, and we have made this conclusion. So the population, the accuracy in the population also will be 64%. Anytime we have n words, 0.64 n words will be tagged correctly. So this is this is the claim, and the questions are the following based on the claim. Can we trust this result? Will the value of 64% hold out on future test data also? This is informal question number 1. Informal question number 2, which is slightly little more specific, is that is the named entity identifier doing anything better than random guessing? Okay, so is there a solid algorithm behind this tagger, which may be rule based or feature engineering based, that is classical machine learning, or purely end-to-end raw data triggered system, which is a deep learning based system ideally? Now, is there an algorithm which is driving this named entity identifier? And we've can formulate this question much more formally in terms of the understanding of hypothesis testing. Determine if the result is significant at 10%, 5%, and 1% level of significance. This is more technical, and this pertains to what is called test of significance. And our discussion is focused on tackling this question formally. Okay, so this is the motivation. Now you have understood the situation. If there is any question at this point of time or comment, do ask, because we'll base our further discussion based on this data. No question, comment? Okay. And you can, of course, write your questions, comments on the chat box. So to concretize the situation a little more, if the input is in the recent address to Congress, the US President Biden had two ladies, Pelosi and Harris, sitting behind him. So this example was created when these US elections were going on, and the president and vice president were elected already. So the output would be in is 0, the is 0, recent is 0, address is 0, 2 is 0, Congress is 1, because this is the name of the party. The is 0, US is again 1, US is name of a country, president is 0, Biden is 1 again. Okay. Now, this is the way the tagging is done. Of course, some of you who are doing the NEI assignment might come back and say that the whole entity, US President Biden, should be looked upon as a named entity. So you should have 111 there. Okay, so let's not worry about the named entity property as such, but look at how hypothesis testing and test of significance is done. So this is the input-output situation. So again, going back to the question, on the face of it, the tagger accuracy as evidence from the data is 32 by 50, which is 64%. So emphasis is on data. Now we have to compare this with random guessing. And the named entity identifier, which is based on random guessing, has the very, very simple experimental platform. The named entity tagger just tosses a coin. If head appears, then the coin is tagged as name. Tail appears, the token is the token is tagged as not a name, 1 or 0. So what we want to test is internally, is the named entity identifier doing random guessing or doing something better? Okay, so so this is the question. Now, what instruments do we have to tackle this question? Now, the accuracy is 64%. Is the accuracy really 64%? Will it hold in any kind of future test situation? That question has been now slightly modified, and we are asking, is the tagger doing random guessing? So that means we are pitching the accuracy against 50%. Okay, if it is a uniform unbiased coin, then we know that there is 50% probability of head, 50% probability of tail. So given the data, 50% of the time, 50% of the tokens will be tagged as name and 50% as no name. Okay, if we go by a random guessing algorithm based on unbiased coin. Okay, so if we perform the experiment sufficient number of times, sufficiently large number of times, that means if we look at a, let's say 1 million token corpus, then we have to toss the coin 1 million times. And as you know, as the number of experiments increases, the probability will tend more and more towards 0.5 if the coin is unbiased. This you know, right? Now, more the data, more will be the behavior of obtaining 50% named entities, 50%, non-name entities. Okay, if this is the algorithm we are following. So I think the situation is clear to you. And also those of you who are slightly, discerning with respect to this discussion, I think will agree with me that we are pitching our observation against a baseline now. Our baseline algorithm is a random guesser algorithm. Okay, and we want to see if our named entity identifier is better. Okay, better than random guesser. What does it mean? Our baseline algorithm is an algorithm based on tossing of an unbiased coin. Okay, so we have two algorithms. Algorithm A, which is the algorithm behind this current named entity identifier, and an algorithm which is based on tossing of an unbiased coin. Okay, so your baseline is random guessing, right? So by the way, random guessing nobody uses for designing an algorithm. This is never a case in practice, but still it is an extremely good baseline platform to compare our algorithm against. Okay, so this is it. Now we want our named entity identifier to be better. Notice the term better than a random guesser. So is there any question on this baseline issue now? Because in machine learning, baseline is so important.
Yes, sir. I have one question.
Yeah.
So we have the probability of head and tail as 50%, but how does that map to accuracy of the data being 50% if we do random guessing? Let's say we guess 1 for all the not named entities and 0 for all the named entities. Suppose in a hypothetical scenario, through that tossing of coin, then the accuracy would be entirely 0, right?
No, but you see, the point is that if there are 1 million tokens in the corpora, I'll have to make 1 million tosses.
Yes.
Right. So 100,000, 1 million, 100,000, no, 1,000. So 1 million. Okay. So 500,000 of those outcomes will be 1.
Yes.
Okay, and 500,000 will be 0. So now, now my claim is that the accuracy of the system is 50% based on my observation. Okay, and I have another named entity identifier which has a different accuracy. So I am these are all claimed accuracy. Okay, these are claimed accuracies, and I'm not. And I think I understand your point. You're saying that you have your accuracy is always measured against gold standard data. So where is the gold standard data? You're not mentioning any gold standard data at all.
Yes.
Okay.
Yes.
So what I'm saying is that I observe how many times the named entity tagger has produced named entities. Okay. Okay. I think I see. What you're saying is that I found that 32 are correct here, correct, and 50 are, and 50 is the total number of data. So the observation is that 32 is correct, right? 32 is correct. So, okay, there is gold standard data. I'm sorry. Yes. So you have a gold standard data and you have found out that 32 are correct. And therefore 64% is my, okay. Now, how does it pitch against the random guesser algorithm is what is your question, right?
Basically, so suppose I am predicting that at a point it is 1. Suppose the
Hmm.
head is giving 1. But then this 1 has to correspond with the gold standard data also. That if this 1 corresponds with 1 in the gold standard data, then I can say that this random guess is correct. Uh, So if that is also a conditioning that I have to do. So I'm not understanding how we can directly say that 50% head is equivalent to 50% accuracy.
I see. Okay. So, so now let's change the question slightly. Let's assume that the named entity identifier is just doing random guessing. Okay, the named entity identifier is doing random guessing, and then let us see the consequence. Maybe I'll have to revisit my baseline comment and so on. So we are comparing, no, we are trying to find out if the named entity identifier is doing random guessing or not. Okay. And now if the algorithm is that I just toss an unbiased coin, and anytime I get a head, I'll tag that token as named entity, otherwise not. Then okay, then it is true that 50% of the time I'll produce named entity, and 50% of the time it will be non-named entity. So how does it map to accuracy is your question actually.
Yes.
Right. Okay. Okay. So okay. So mapping it to accuracy is the question. Okay. Let me come back to that later. So
Okay, sir.
uh, I do a bit of rolling back and then proceed with the discussion. Okay. Let's see.
Sir, I'll also
Understand it?
add one point. I'll also add one point to Saruv's question. Just
Yeah.
head is not giving to accuracy also. Even if you are tossing a tail, and if ground truth is no name and it's a tail, it's also contributing to accuracy. It's not only head.
Acha. So I think accuracy is the thorn in the flesh now. So I'll remove the discussion on accuracy now for the moment. I'll just say that I want to establish or demolish the hypothesis that my named entity identifier is a random guesser. Okay, so so this is the hypothesis I want to establish or demolish. That means because I want to buy this named entity identifier from a company which has created this. Okay, and I want to buy this, and I want to check that it is not simply doing random guessing. Okay, so now my hypothesis is this: the named entity identifier is doing random guessing based on the tossing of an unbiased coin. This is my hypothesis, and this hypothesis I want to either reject or accept. Okay, so that I think you are able to accept. Okay, don't worry about accuracy now. Let's accept that now. Okay, now we come to some terminology and definition that we will require. First and foremost, we have to form what are called null and alternative hypothesis. So there is a notation for this. H0 is called the null hypothesis, and I have stressed this many times before, that null hypothesis is created with the explicit purpose of finally demolishing it, okay, based on the data that is in front of us. So that is why the name null hypothesis is given. The hypothesis is nullified going forward. And this is the hypothesis that we want to reject. There is some more notation, HA or H1. This is called the alternative hypothesis, which is opposite of the null hypothesis, H0. And we use something called sample statistics in trying to reject H0, the hypothesis. So it is really a situation of proof by contradiction or refutation. Let me first put forward the hypothesis, then also the null hypothesis, and my goal will be to reject this hypothesis based on the observation or the data in front of me. This is the methodology. Okay, and this rejection or acceptance of the hypothesis is not absolute. Okay, it is not black and white, which is why probability is invoked here. Okay, so let's see the mechanism. We need little more terminology. what is called type 1 and type 2 error. Type 1 and type 2 errors are always with respect to the null hypothesis. Okay. So again, we can draw what is called the contingency table, which you people also create all the time. Another name for that is the confusion matrix. Now this is in the form of what is called a contingency table. So I have formed a hypothesis. This is the H0, and columns are called accept or reject as per data. And the hypothesis can be actually true or actually false. Actually means independent of observation or data. Some oracle, some entity which has the knowledge, intricate knowledge of the situation, not really dependent on the observation of the data in front of me. So that tells me whether the hypothesis is actually true or false. And as per data, we can say I accept the hypothesis or reject the hypothesis. Now, 4 situations can happen. The hypothesis is actually true, okay? And from the data, we are able to accept the hypothesis. So that is a case of no error. Now, hypothesis is actually true, but as per the data, I am not able to accept it. I have to reject it. Okay, then it is called type 1 error. The hypothesis is actually false, but I have accepted it as per the data. My data doesn't allow me to reject it. I have to accept it. Then this is known as the type 2 error. And if the hypothesis is indeed false and based on the data I'm rejecting it, then there is no error. So as usual, the diagonals are no error cells, and the off diagonal cells are type 1 error and type 2 error respectively. So can we relate this table to false positive, false negative? Okay, the hypothesis is actually true, but it is rejected based on the data. Is it false positive or false negative? And the complementary case of type 2 error, is it false positive or false negative? Okay, think about this point maybe towards the end of the lecture, or in another discussion we'll come back to this. But type 1 error, type 2 error are coming from probability theory, a very old notion. Okay, very old notion. So we would like to familiarize ourselves with type 1 error and type 2 error. Now, can we relate these to, some practical situations? Okay, so a patient actually has cancer. We many times resort to this example, not a very pleasant one, but based on the pathological data, based on case history, family history, environmental data, and so on, all these is my data. And based on the data, I reject the hypothesis that the patient has cancer. But in reality, actually, the patient has cancer. So then I am making a type 1 error, and that would be very dangerous because going forward, the patient would die. Okay. What is the type 2 error case? The patient doesn't have cancer actually, but the data forces me to say that the patient has cancer. This is type 2 error. And this is not dangerous. The patient will remain healthy as far as the cancer situation is concerned. But it will be a big anxiety, mental anxiety, as well as tremendous amount of expense on medical investigations. Okay, so type 2 error in this case is not as serious as type 1 error. Both of them are costly. One is life-threatening. The other is a strain on finance and mental peace. Okay, so this point is clear. Any question or comment at this point? So I want to take a stand here that in case of cancer, type 1 error is much more serious than type 2 error. can you think of an opposite situation where type 2 error is more serious than type 1 error? Okay. Again, you can keep this question in mind and we can come back to this point. Okay, so let's proceed. Type 1 error, the hypothesis is actually true, but we are rejecting it. Okay, and we'll keep this type 1 and type 2 error in mind. So they, by the way, arise, type 1 and type 2 error, they arise after we have decided the null hypothesis. Okay, so everything starts with the null hypothesis. So we have discussed at least 3 or 4 very important terms: null hypothesis, alternative hypothesis, sample statistics, then type 1 error, type 2 error. Five important terminology. Any doubt or question with respect to these definitions? Okay. Now we come back to my NEI problem. Here I'm saying that the named entity identifier that I'm going to buy from the company is actually nothing but a random guesser. Okay, and I don't want to buy if that is the case. But somehow I trust the company and I want to reject this hypothesis. Remember that null hypothesis is always created with the aim of nullifying it going forward. Okay, so the probability of the tagger labeling correctly, if it is a random guesser, then it is 50%. I think you will come back, Nihar and Swaroop and maybe others also will come back and say that no, we do not understand this. The moment you say correctly, you are referring to a gold standard data. But allow me to proceed because I want to show you the mechanism by which hypothesis is rejected or accepted. Okay, so this point about accuracy will come back a little later. So I'm saying that
Okay, sir.
I'm saying that the probability of the tagger labeling correctly is 50%, and this is equivalent to random guessing. Maybe the word correctly is the problem here. Okay. We introduce more terminology, which is confidence interval. Okay, so the confidence intervals are given as 90%, 95%, and 99%. And now the process can start. Of course, now we have introduced more terminology, and they are so important for hypothesis testing. So let us understand what we mean by these intervals. Now, if I have fixed the null hypothesis H naught, where P is equal to 50%, then I want to make sure that I'm buying a good named entity identifier. I want the P value to be greater than 50%. Okay, so we have to choose what is called the one-tailed test, the greater than test, since we want the tagger to perform with high score. Okay, so more terminology, more definitions are coming in. So we need to go slow and see what all this means. So we continue the discussion, and if indeed there is 50% probability, if indeed the named entity identifier is just doing random guessing, then there is 50% probability that a token will be identified as named entity. So so then if n tokens are given, then 25 of them will be tagged as named entity. Okay, so this is mu. Mu is equal to n into p. 50 tokens have been given. P is the probability of being labeled as named entity or not. So 50 into 0.5 is 25. So this we have to accept as the population mean. Okay, and the standard deviation is n into p into q to the power half. This is as per the binomial distribution. So 50 into 0.5 into 0.5, square root of that is 12.5 square root, which is 3.54. What does it mean? Okay, this is explained in the next slide. Let us choose many samples of size 50. And if the null hypothesis is indeed true, that is random guessing is indeed true, we will get on the average 25 heads for each sample. Okay. And of course, there will be variations on this number because these are sets of 50, 50, 50 tokens. There will be sometimes 25, sometimes 24, sometimes 27. Okay. So these many heads will appear in different samples of size 50 each. There will be some variation, and we know that the standard deviation is going to be 3.54. This is as per Bernoulli binomial distribution. So those results we can revise later. You can also go back and revise those results. Given the sample size n, okay, each of the trial being a Bernoulli trial, that means it has only two outcomes. The probability of one outcome is p. The probability of the other outcome has to be 1 minus p, because only two outcomes are possible. Such trials are called Bernoulli trials. Okay, a random experiment where there are only two outcomes possible is called a Bernoulli trial. And p is the controlling parameter. An example of Bernoulli trial is coin toss, the outcome coming from a coin toss. So now if we have n Bernoulli trials, okay, and if p is the parameter controlling the trial, then the mean value is n into p, this given notation mu, and np is the population mean, and the standard deviation is square root of n into p into q, q being 1 minus p. These results are known from binomial distribution Bernoulli trial. Okay, so coming to our problem situation, if the named entity tagger was indeed doing random guessing, then on a sample of 50, okay, we will get on an average 25 named entities. Okay, let's forget about accuracy now. Let's forget about the gold standard data and so on. This is what I'll observe. But what I've observed is that out of 50, I have obtained 32 named entity. Okay, so that means most probably the named entity identifier is not doing random guessing, because if it was doing random guessing, then on samples of 50, I will get the number of named entities as 25 on an average. Okay, this is what will happen. Okay, so I'm not really referring to the accuracy now. Maybe I should correct my standpoint here. Is it or is it not doing random guessing? So I think the situation has become now quite clear and intuitive. Only thing is that we have to place it on a formal footing. So let me summarize the situation and see after that if you have any questions. The situation summary is this: that I want to test whether my named entity identifier is doing random guessing or not. If it was doing random guessing, then the probability of tagging a token as named entity would be 50% if the random guessing algorithm is toss an unbiased coin and tag the token as named entity if the outcome is head. Okay, so then on an average, I will tag the tokens as named entity 50% of the time. This is true. Okay, and to investigate whether that is the case, I have decided to take sample of 50, size 50, and there I have found it is 32. Okay, the number of times it is tagged as named entity is 32. Okay, And of course, I think gold standard and accuracy was somewhat misleading. I have a comparison situation here, okay, independent of gold standard or accuracy. I think that correction I have to do. Okay. So, so now so now the situation is this. I have made the hypothesis that it is doing random guessing, but I have found that the number of named entities is 32 out of 50. Okay, and that also happens to be the correctness situation. Okay, so now based on the data, do I accept or reject the hypothesis? I want a system for doing so. Okay, any question at this point of time?
At this point of time, can we reject straight away that the given system is not random guesser if the number of name entities or non-name
Right.
entities
So
are
can we reject straight? Okay. So that is the question I was expecting, and that is the right question. Yeah, because I've got more than 25 named entities, and they also happen to be correct. Okay, they also happen to be correct. Can I not reject the hypothesis outright? Okay, it depends on my tolerance level. Now comes the second part of the discussion. It depends on my tolerance level. It depends on how much of type 1 error I am prepared to accept. Okay, let's proceed. So the intuition that if most of the time, if I see that the number of named the number of correct tokens is more than 50%, okay, I will have a suspicion that this hypothesis is not true. I should reject that hypothesis. So what is the formal way of doing so is our point of the discussion. Okay, so we have found out the best possible guess for the population mean, best possible guess for the standard deviation. This is based on maximum likelihood estimate, and that is also another important discussion. Okay, you will come back and tell me that, well, why do you say that the population mean is 25 based on the fact that 50% is the probability of success? Why do you say that the standard deviation is NPQ square root? Why do you say that? This is theory of binomial distribution, Bernoulli trial. Okay, that is another box which we need to open, or if you already know, it is fine, it's open for you. Let's see. Now, to systematize this discussion, we have to go back to our old friend, normal distribution and area under the normal curve. So here we revise the things that we know about normal distribution. So normal distribution is a bell-shaped curve, and the total area under any probability distribution which is continuous is 1. Okay, you integrate from minus infinity to plus infinity, the area, the integrand will come out to be 1. Now, important practical things which are known are that from minus 1 to plus 1, this is standard normal curve. The mean is 0 and the standard deviation is 1. This is known as the standard normal curve. So from minus 1 to plus 1, the area is 68%. From minus 1.96 to plus 1.96, the area is 95%. From minus 2.58 to plus 2.58, the area is 99%. Okay, so in a standard normal curve, I do not need to look beyond minus 2.58 or plus 2.58. The probability of those data points will be extremely small. Okay. So this is the area under the normal curve, which we know from our study of property of normal distribution. Now, this is a useful table test type versus confidence interval. So if we have what is called the two-tail test, then the 90% of the area is from minus 1.65 to plus 1.65. 95% we just now saw is minus 1.96 to plus 1.96. And 99% is minus 2.58 to plus 2.58. Now there are two more tests called left tail and right tail test. So the area from minus 1.28 to plus infinity, minus 1.28 to plus infinity, the area is 90%. Minus 1.65 to infinity plus infinity, the area is 95%. Minus 2.33 to plus infinity, again, the area is 99%. So if you do not consider the areas on both sides of 0, but if you want to consider only the area on one side, okay, then only up to plus infinity or only up to minus infinity, then these are the numbers. Okay, so similarly, minus infinity to 1.28, the area is 90%. Minus infinity to 1.65, 95%. Minus infinity to 2.33, 99%. Okay, so right tail, left tail, and two tail test are test types, and the confidence intervals are the intervals which accumulate that probability. The significance of this becomes clear as we proceed. They are useful for our discussion. We remember our original question. I am getting more than 50% heads, more than 50% named entity tokens, and they happen to be correct. Okay, so then can I not reject the null hypothesis? This is the question. So this pictorially depicts the areas which we have already discussed. Now the significance of the level of significance alpha. So a little more notation here or terminology. When we have 90% confidence interval, alpha is 0.1. Okay, so the area beyond 95% confidence interval is beyond 90% confidence interval is 10%. So this alpha, so this is expressed by saying the level of significance alpha is 0.1. And this corresponds to the situation of prepared to tolerate 10% type 1 error. So the probability of wrong rejection of H naught is 10%. Okay, many things are being said here. You will have to connect those dots. 90% confidence interval corresponds to significance level of 0.1. And this means we are prepared to tolerate 10% type 1 error. That means if we reject H naught, the probability of this being wrong is 10%. Okay, and if 95% is the confidence interval, then the level of significance is 0.05. We are prepared to tolerate only 5% type 1 error. And if I reject H naught, the probability of that being wrong should be 5%, only 5%. Okay, and 99% confidence interval, there the level of significance is 1% or 0.01. We are prepared to tolerate 1% type 1 error. The probability of wrong rejection of H naught is 1%. So as we increase the demand on the confidence interval, that it should become more and more, then the level of significance also keeps on decreasing. That means our tolerance with respect to error, type 1 error in particular, also the tolerance also goes down. We become more and more demanding with respect to the accuracy. So type 1 error, remember, is the probability of wrong rejection of H naught. Wrong rejection. Okay. Now H naught is something we want to nullify. We really want to nullify H naught. That means we want to reject it. and that rejection should not have error. Okay, if rejection has error, then it is called type 1 error. And if the probability of that error is 1%, then we are very, very intolerant with respect to error. Okay, so many things are being said, and we have to connect those dots. So that's why hypothesis testing, test of significance, it doesn't harm if we go back to it again and again through different problems. Significance of the level of significance. As alpha decreases, the test becomes more and more stringent, that is strict and demanding. Okay. Okay, so this we have discussed already. Now back to the NEI problem. So observation was this. There were 50 words and the correct tags, correct after some time. We have tagged 32 as, we have tagged these words as named entity and no named entity. Out of them, correct tags are 50. Okay, combination of both named entities and non-named entities. So this is the observation, 50 words correctly tagged 32. So accuracy as per data is 64%. And we would like to compare this with random guessing. Okay, so this we have discussed. Now H naught is the null hypothesis that the named entity identifier is doing random guessing. Okay, and that we want to demolish with confidence intervals as 90%, 95%, and 99%. Okay, so two things we have to start with. First of all, start with the null hypothesis, and also specify right in the beginning what is your tolerance level. Okay, so that means you want confidence intervals to be 90% or 95% or 99%. This corresponds to my tolerance with respect to type 1 error. So after doing these two things, null hypothesis and specifying the confidence interval, there is a mechanical procedure to follow. So the foundation for this is that if H naught is not consistent with the data, we must reject the H naught. So under the assumption that H naught is true, if some property of the data called data statistics does not hold, we should reject H naught. And that means if H naught doesn't entail the data, we reject H naught. This is the foundation. Okay. So now we have given H naught that it is doing random guessing. Named entity identifier is doing random guessing. So here my alternative hypothesis will be opposite of that. It is not doing random guessing. But additionally, there is a demand from the performance point of view. I want the accuracy to be more than 50%. Okay. So here we have to choose what is called the one-tailed test, the greater than test, since we want the tagger to perform with high accuracy. So let's see. We have the mu population mean as 25. This we have understood. If we take samples of size 50, then on an average we will get 25 correct tags, and then the population mean will be this as per maximum likelihood estimate, and the standard deviation is 3.54. Now we have another instrument available to us. This is called the Z test. So we have observed the number of correct tags to be 32. Okay, and the population mean under null hypothesis. If the null hypothesis was true, okay, then the population mean is 25. Okay, here of course you will come back and ask, how can you say that 25 would be correct if the null hypothesis was true? Okay, let's see the mechanism first. You have to take the observation value of the random variable, the number of correct tags. You have to subtract the population mean from this. You have to divide it by the population standard deviation. That gives rise to what is called a standard normal variable, a random variable which follows the standard normal distribution. Mean 0, standard deviation 1. And for 32, the Z value is 1.98. Okay, so this is called the observed Z value. So 32 has been converted to a Z value, which is 1.98. Now I compare observed Z value with the critical Z value. What is critical Z value? This is decided by my tolerance level or the interval that I have specified. So if I had 90% confidence interval or level of significance is 10%, then the critical value of Z will be 1.28. Okay. And if 95% confidence interval, then the critical value of Z will be 1.65. And if we want 99% confidence interval, then the critical value of Z will be 2.33. All are one-sided. Okay. So I'm presenting mechanically what is done. It is so mechanical that now we know there are hypothesis testing packages, okay, which give you these critical values and level of significance. Once you specify the level of significance and the observation, then it can give you whether the null hypothesis is valid or not at what significance level. Very mechanical procedure. Now, critical value we have to examine for at least for students who are new to these discussions. So now ZO, which is 1.98, is greater than critical value of Z, which is 1.28 for 90% confidence interval. Now, the convention is that if the observed Z value is more than the critical value, then we can reject the null hypothesis. Okay, this is a mechanical statement, but the reason is there. So now we can reject H0 and we can accept HA. In other words, the data in conjunction with the confidence interval suggests that the NEI tagger is doing better than random guessing, and my probability of wrong rejection will be 10% only. If you are prepared to accept 10% type 1 error, then H0 can be rejected. If you are prepared to tolerate that in 10 out of 100 cases will go wrong, then we can reject H0. That means we can say that the named entity tagger is doing better than random guessing. Suppose the named entity identifier is actually doing random guessing and we reject H0. Then we say that no, the named entity identifier tagger is not doing random guessing, but internally employing an algorithm that is better than random guessing. Okay, as per the confidence interval, I am prepared to tolerate 10% type 1 error. And as per data, the probability of going wrong with the stand no, the named entity identifier tagger is better than a random guesser is at most 10%, because ZO has entered into the critical region. Okay. Now, when Z observed is more than ZC critical, why can we reject? That is another discussion which needs to be conducted. Now, what if my tolerance level goes down? Okay, we have observed that Z value for 32 is 1.98, and for 95% confidence interval, ZC is 1.65. This is actually 95% confidence interval. So now HO can be rejected and we have to accept HA. That means the data in conjunction with confidence interval suggests that named entity identifier tagger is doing better than random guessing. What happens if we demand 99% confidence interval? Now my tolerance limit is very low. I'm not prepared to tolerate wrong rejections. Okay. Now Z critical will be 2.33 and Z observed does not enter the rejection region. So Z is less than ZC. Now H0 cannot be rejected On the basis of the data and confidence interval, we cannot rule out the possibility that named entity identifier is just doing random guessing. Okay, so you see, then which implication is correct? All implications are correct. Okay, we are about to finish our time now. Let's have this discussion. All implications are correct. Depends on our tolerance level, how much type 1 error we are prepared to accept. Only one error case out of 100, it is very stringent. 5 errors out of 100, less stringent. 10 errors out of 100, much less stringent, more permissive. Okay, so now we should conclude, and we have this interesting situation here. Our goal was to see whether the named entity identifier is doing anything better than random guessing. Is there a proper machine learning algorithm underlying the named entity identifier? Is the NEI based on a good sound algorithm? That was my goal. So I took 50 tokens corpus and asked this named entity identifier to tag it. 32 of them were found to be correct. So I went with the preconceived idea that the named entity identifier is doing random guessing only. There is no algorithm behind it. The company has not invested any money to create that named entity identifier. So now the data is 32 out of 50 is correct. So can I reject or can I accept the hypothesis? Just based on the data, you cannot make this decision. It also depends on how much error you are prepared to tolerate. You see, data and your tolerance level or the confidence interval that you are prepared to accept. The confidence interval is always at the backdrop, against the backdrop of normal distribution. This raises more question. What is so sacrosanct about normal distribution? Why are you invoking normal distribution? Again, there is a theory behind it, which we had done before. Central limit theorem is at play here. So the interesting point, the main message I'm trying to convey here is that you do form a hypothesis, and there is a particular demand on the hypothesis you form. That hypothesis you endeavor to reject. That's why it is called a null hypothesis. You endeavor to reject this based on the data. You cannot reject it black and white. It depends on how much error you are prepared to tolerate. Okay, it is decided by the type 1 error, this table, the contingency table. If your tolerance level is high, you may be able to, you may not be able to reject the hypothesis. If the tolerance level is low, you may have to reject the hypothesis. But there are two forces at play here, the data or the observation and the confidence interval or the level of significance you have set up for yourself. How much of error are you prepared to tolerate depends on the problem situation. Cancer patient, one case. Output from a Maruti car plant, another situation. Okay, visa application, accept or reject. Loan application, accept, reject. Depends on the situation, depends on the problem. And why can't you outright reject it or accept it based on what is in front of you? That is because from sample to sample, the observation will vary. Okay, so there are many things coming into the perspective, and we have to create a framework out of many considerations. I'll stop here with just one final remark. Data and how much error you can tolerate, and the hypothesis you want to actually demolish. Okay, I'll stop here. Our time is up. any question, comment? I concede that I have not answered your question about accuracy when it is doing random guessing. I'll do it next time. And then let me see if there are any other questions or comments.
So one question, suppose in that case that we are ready to accept 10 errors out of 100, what does that error mean? Does it mean that our NEI tagger is not good? Does it mean that the NEI tagger in those 100 cases would be random guessing tagger? Does it mean that?
I lost your last part of the statement. Come again?
Yes, sir. Basically, we are saying that 10 out of 100 are error cases in 10% significance level. So does it mean that in those 10 cases, the NEI tagger would be no better than the random guesser?
So if I have heard you correctly towards the end, I am prepared to tolerate 10% type 1 error. Okay. What does it mean? It means that if I reject the null hypothesis, okay, what is my null hypothesis? My null hypothesis is that the named entity identifier is nothing but a random guesser. So I reject it. I say that no, the named entity identifier is better than a random guesser. There is an actual algorithm, maybe an SVM based algorithm behind it. If it turns out, then in 10 out of 100 cases, okay, it is actually a random guesser. Okay, then I have made the type 1 error in 10 out of 100 cases. Okay, say me, my friend, they go and buy this named entity identifier many times over. So this gets sold many times over. Okay, and I have made I have been wrong 10 out of 100 times. Okay, then this is the case of 10% type 1 error. So your question was, what does it say about the quality of the named entity identifier actually, right? Is that your question?
Yes, sir. In those 10% of the cases.
Yeah. So this is the this is the beauty of probability. So there is nothing called what is the absolute quality of the named entity identifier. It depends on the observer in the sense that how much is the error tolerance limit of the observer, okay, and what is the observation in front of me. And then you will say that, but in actuality, I'll have to run that named entity identifier, and I'll have to use the output for downstream application. Okay, so there is this practical situation of actually running the NEI and doing downstream application. So what is its absolute quality? There is nothing called absolute quality. Okay, it depends on again the user of the system and the data in front of him. Okay, so the notion of absolute quality is actually an illusion. When we probe deeper and put it to very stringent test, all the sense of absoluteness disappear. Yeah. Okay, any other question or comment?
Yes, I have a confusion. Like in given example, like we have 32 correct sample.